Hearty welcome to the Math Revision Made Meticulous video series. Topic Relations and Functions. Subtopic Types of Relations. Revision, as the name suggests, means looking back over previously learned information, ensuring that it is clear and fresh in the mind. 5 questions per video from selected topic is presented at this video series. The steps in answering the questions are supported by the ideas used for getting the answer. Let us see what is a relation which you already have seen it in class 11. Let A and B be two sets. Then a relation R from capital A to capital B is a subset of A cross B, where A cross B is the cross product. Relation is collection of ordered pairs in which the two elements are related by predefined relation. Relation between two elements is expressed as a formula or as a statement. Let us try to recollect some relations which we have seen in class 11. Examples. Let us go for relation R defined on set A 1, 2, 3, 4, 5 as A is related to B, that is A comma B belongs to R if A is greater than B, or A or B if A is greater than B. Now which elements will come now? We have to select some elements now. Now the set R will be 2, 1 because A should be greater than B, 3, 1, 3, 2, 4, 1, 4, 2, 4, 3, then once again 5, 1, 5, 2, 5, 3, 5, 4. That's it. The first element position should be greater than the second element in that ordered pair. That is the relation defined. Let us have one more example. Relation R in the set of integers given by A comma B 2 divides A comma B. Now it will be infinite because 0 comma 2 0 comma 4 and so on, then 1 3 1 5 and so on, then 0 minus 2 0 minus 4 and so on. It will have infinite. Therefore a relation can have finite number of sets or infinite number of sets. Let us go to one more example. T be the set of all triangles in a plane with R as a relation in that capital T given by T1 is related to T2 if T1 is congruent to T2. This is another relation. We are collecting all the triangles which are congruent to each other. Well, now in class 12 we are going to see types of relation. In class 11 we have seen what do you mean by a relation and some examples you have seen, and you know what is the domain, what is the range and so on. In class 12 we are going to see about types of relation. Let us see what is a reflexive relation. A relation R on a set is said to be reflexive if every element of A is related to itself. The relation is reflected, therefore it is called a reflexive relation. Thus R is reflexive when A is related to A or A comma A belongs to R for all A. You should be very careful. This should happen for all the elements of the set. The above condition is for all the elements of the set. A relation R on a set A is not reflexive if there exists an elements, at least one element you are able to identify such that it is not related to itself, then it is not reflexive. Remember, the condition is for all the elements of the set. Okay. Let us go for what is the working rule to check the reflexive relation. If the relation is finite, suppose if you are given that relation set is a finite and A comma is an element for A is a given set, you simply check whether A comma is available there. Then if the relation is R which is given as infinite, then take an element, then replace B by A in the given definition, check whether it is valid, and if valid then reflexive, if not valid not reflexive. Therefore we are here given two ways of checking a reflexive relation. Suppose if it is a finite set or it is an infinite set. Let us take some examples. Here I have taken 1 2 3 4 5 the same thing, A is greater than B. Here you have taken 2, 1, 3, 1, 3, 2, 4, 1 and so on. But here 1, 1 is not there, 2, 2 is not there, 3, 3 is not there. therefore 1 is not related to 1, therefore it is not reflexive. I actually told one element is enough. 1 comma 1 not belongs to R, 2 comma 2 not belongs to R, like that. No need to define again and again. 1 comma 1 not belong. One element is not there because 1 is not greater than 1. 1 is equal to 1. But it is not reflexive. Let's take another example. 2 divides a minus b. We are taking all these elements over here, and a comma, if you take a any integer, a minus a is 0, it is divisible by 2. Therefore a comma a belongs to R, therefore R is reflexive. When you take another example where set of all triangles in a plane, when first one is related to congruent to the second, then take a triangle. It is clear that the triangle is congruent to itself, therefore T1 is related to itself. T1 comma T1 belongs to R, therefore R is reflexive. Let us move on to the next type, symmetric relation. A relation R on a set A is said to be symmetric if and only if A belongs to R implies B comma A belongs to R. That is, when A is related to B, B is related to A. It is called symmetric for all A comma B belongs to A. Now we are writing like this also. A or B implies B or A. That is, A related to B implies B related to A for all A comma B belongs to capital A. What is the working rule for it? Suppose if it is finite, you check whether A comma B, for every A comma B, B comma A is also there in the set. For example, 1 comma 2 is there, 2 comma 1 should be there. If 3 comma 5 is there, 5 comma 3 should be there, like that. Suppose if it is infinite, suppose if the relation is infinite, take 2 elements from the given set, then assume A comma B as per the given definition, then replace B by A and A by B in the given definition. That is, you replace them, just interchange their places, and check whether the given definition is valid. If it is valid, then it is symmetric. Not valid, not symmetric. This is the rule for check for finite sets and for infinite set. Let us go for one example. The same example which we have seen, that R is 1, 2, 3, 4, 5, and we have taken that A related to B if A is greater than B. Here 1 comma 2 is there and 2 comma 1 is also there. Okay, 1 comma 2 belongs to A and 2 comma 1 is there, but 1 comma 2 is not there because 2 is greater than 1 but 1 is not greater than 2. Therefore, hence R is not symmetric. Here we are checking whether for 2 comma 1, 1 comma 2, similarly 3 comma 1 is there but 1 comma 3 is not there, 4 comma 1 is there, 1 comma 4 is not there. It is enough you prove one element is not satisfying the property of symmetric nature. Let us go to the next example. We have taken 2 divides A minus B. Then let A comma B belongs to R, which means 2 divides A comma B. 2 divides B minus A also. Therefore, B minus A belongs to R. Therefore, if you take A minus B belongs to A, for A comma B, the integers, if A is related to B, B is also related to A. Therefore, R is symmetric. Here we have proved it for an infinite set. Now let us take this third example, that is set of all triangles. First triangle is congruent to the second, that is a given relation. Therefore, I take T1 related to T2. Let me check whether T2 is related to T1. Well, if first is related to the second, second is related to the first, because it is a congruent nature. First triangle congruent to the second, therefore second is congruent to the first. Therefore, we are getting that it is a symmetric relation. Good. Let us move on to the transitive relation. A relation R on a set A is said to be transitive. The relation is translated, therefore it is transitive. A comma B belongs to R and B comma C belongs to R, then A comma C belongs to R. This transitive relation, you have seen it in lower class. When A is equal to B and B is equal to C, then A is equal to C. And if LHS is equal to RHS in equation 1, again RHS is equal to some other thing, then you have equated from equation 1 and 2, LHS equal, therefore RHS equal. And you have proved it in parallel nature also. First is parallel to the second, second is parallel to the third, therefore 1 and 3 are parallel. But we have already used this transitive relation in lower class. Therefore, relation is first is related to the second, second is related to the third, therefore 1 and 3 are related. We are writing it as A or B and B or C. That is A related to B and B related to C. Therefore, we are concluding that A related to C. Good. We are now going for working rule. If R is finite, check A comma B and B comma C, and also A comma C are the elements. If all are elements, then it is transitive. Check whether A comma B, B comma C and A comma C is available. If A comma C and B comma C are available, A comma C should be available. Okay, well, if it is infinite, take three elements. Assume A comma B belongs to R and B comma C belongs to R as per the given definition, and you check whether A comma C belongs to R using the above result. And remember, you have to prove it. You have to prove it. If it is valid, then transitive. If not valid, it is not transitive. If the relation is transitive. Okay, well, now let us go for examples now. For R defined on the set of real numbers, and we are taking A, B, C belongs to A comma B belongs to R because A is greater than B. B comma C belongs to R because B is greater than C. Therefore, which is greater now? A is greater. For A is greater than C, therefore R is transitive. You know issue now? First is greater than the second is greater than the first, therefore first is greater than the third. Okay, well. We are moving on to the transitive relation, which is vacuously true. It is very, very important. This one you have to note down. Let a relation R on A is defined such that A comma E is in R, but B comma C is not in R. Be careful. If you are checking whether A comma B is belong to R, you are seeing, but B comma C you are not able to identify in the given relation, then we cannot prove A comma C belongs to R. That is why in such cases, it is assumed that transitive relation is true. Again I repeat, A comma B is available, but B comma C is not available. A is related to B, but B is not related to anything. In that case, it is taken that it is transitive relation is true. Let us take one example now, how it is vacuously true. Relation R is in set of natural number defined by x comma y, y is equal to x plus 5 and x is greater than 4. And I am getting 1 comma 6, 2 comma 7 and 3 comma 8. There are the only three elements over here. And 1 comma 1 is not in R, therefore it is not reflexive. And 1 comma 6 is in R, but 6 comma 1 is not in R, therefore it is not symmetric. But 1 comma 6 is there, but 6 is not related to any other element. Therefore, there is no pair such that xy and yz belongs to R. Therefore, this condition is vacuously true. Therefore, R is transitive. Be careful, not reflexive, not symmetric, but transitive. Well, let us move on to questions now. We have to check whether the given relation A comma B, where B is equal to A plus 1 is a reflexive, symmetric or transitive. Finite elements are there, 1, 2, 3, 4, 5, 6, or I am making them. A comma B, B is equal to A plus 1. Therefore, 1, 2, 2, 3, 3, 4, 4, 5 and 5, 6 are elements. First, let me check whether it is symmetric. 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4, 5 comma 5, 6. Nothing is there. Therefore, it is not reflexive. Check whether only 1 comma 1 is not there. Also, you can check and then prove that it is not there. But I have given you all so that you take any one of them, pick anyone. Your lucky number 4 comma 4 not belongs to R, then it is not reflexive. Then let us check whether it is symmetric. No. 1 comma 2 is there, but 2 comma 1 is not visible there. Therefore, it is not symmetric. Now, very clear here. 1 comma 2 is there, 2 comma 3 is there, but 1 comma 3 is not there. Therefore, it is not transitive. Not reflexive, not symmetric, not transitive. Be careful with the transitive. Here, I am able to check 1 is related to 2 and 2 is related to 3, but 1 is not related to 3. Is okay? 2 is related to 3, 3 is related to 4, but 1 is not related to 4. 3 is related to 4, 4 is related to 5, but 3 is not related to 5. Well, I think I am giving so many examples. Therefore, it is neither reflexive, nor symmetric, nor transitive. Good. For this previous problem, neither reflexive, nor symmetric, nor transitive. Well, let us move on to the next question. Show that the relation defined as R is equal to A comma B, A less than or equal to B, is reflexive, transitive, but not symmetric. Here they have given you to prove. Therefore, be careful. You have to prove reflexive, prove transitive, but not symmetric. Clearly, A comma A belongs to R as A is equal to A. There is a less than or equal to is there. Therefore, R is reflexive. Now, I move on to symmetric nature now. When I move on to the symmetric nature, 2 comma 4 is belongs to R as 2 is less than 4. But 4 comma 2 is not in R because 4 is greater than 4. Therefore, not symmetric. When I replace it, A less than or equal to B, B is not less than or equal to A. Well, I have taken one example. variety not symmetric. Now let us check whether transitivity is there. A is less than or equal to B, B is less than or equal to C, therefore A is the biggest number, for A is less than or equal to C is there, for A comma C is an element in the relation, therefore R is transitive. For what is your proof now? Already they asked you to prove it is reflexive, transitive but not symmetric. Let us go to question number 3. You have been given A comma B and A less than or equal to B cube is reflexive, symmetric or transitive. Let us go to 1 by 2 belongs to R. Where I am taking examples. 1 by 2 is greater than 1 by 2 the whole cube. Therefore 1 by 2 and 1 by 2 it does not belong to R. Be careful, 1 by 2 is greater than 1 by 2 the whole cube. Therefore it is not reflexive. Let us check whether it is transitive. 1 comma 2 belongs to R. As 1 is less than 2 cube. 1 is less than 2 cube. But 2 comma 1 is not there because 2 cube is greater than 1. 2 cube is greater than 1. Therefore it is not symmetric. 1 is related to 2 but 2 is not related to 1. Good. Let us go to transitivity. Here we are taking 3 examples, which should be very careful. 3 by 2, 6 by 8, because if you take some examples it may be transitive, but you have to prove that it is not transitive. 3 by 2, 6 by 5 I am taking. 3 is less than 3 by 2 the whole cube, and 3 and 3 by 2 are belongs to R. Again 3 by 2 is less than 6 by 5 the whole cube. Therefore 3 by 2 and 6 by 5 are related, but 3 is greater than 6 by 5 the whole cube. All of you know it, because 6 by 5 whole cube is something 1 point something the whole cube. Therefore first is related to the second is related to the third, but first is not related to the third. Therefore neither reflexive nor symmetric nor transitive. Okay, let us go to question number 4. Before we go for that, let us define one more. As relation R on a set is said to be equivalence if it is reflexive, symmetric and transitive. Just now we have seen problems where we proved symmetric, we checked reflexive, we checked transitivity. Suppose if all the 3 are there, it is called an equivalence relation. In the exam they may ask you to prove that it is an equivalence. You have to prove reflexive, you have to prove symmetric, you have to prove transitive. Let us go for example. Now show that the relation R defined on a set of all triangles where T1 is similar to T2 is equivalence relation, and sometimes they may ask you to prove 3 triangles and check whether which is related to what. Okay, let us see that question later. First let us try to prove that it is first reflexive. Every triangle is similar to itself, therefore T1 is related to T1, therefore R is reflexive. Suppose if you take the first triangle T1 related to T2, T1 is similar to T2, and in turn T2 is similar to T1. All of you know, first is related to the second, therefore second is related to the first, therefore T2 is also related to T1, therefore R is symmetric. First triangle related to the second, also second is related to the first. First is similar to the second as second is similar to the first. Well, now let us go on to proving checking transitivity. I am taking 3 T1, T2, T3. T1 similar to T2, therefore T1 comma T2 I am taking. T2 is similar to T3, therefore I am taking it. But I am able to prove that it is a transitive relation because T1 is similar to T3. T1 and T3 is belongs to R. First is similar to the second is similar to the third, therefore first is similar to the third. It is an equivalence relation. Now let us take 3 triangles. Right triangles are given of the side 3, 4, 5 and side 5, 12, 13 and T3 with side 6. Now from the right angle triangle T1 and T3 I am getting the sides whether they are similar. All of you know for similarity you have to check whether the corresponding sides are proportional. For I get 3 by 6 is equal to 4 by 8 is equal to 5 by 10, therefore T1 is related to T3. But they want whether which is related, whether T1, T2 or T1 and T3. Therefore T1 and T3 are related. They are similar as per the given definition. Here I have used the condition that when 2 triangles are similar, the corresponding sides are proportional. Okay, let us move on to the question from CBSE 2008. Show that the relation A comma B related to C comma D if A plus D is equal to B plus C on n cross n. This is a ordered pair related from one set to another set. Let us now check A comma B belongs to n cross n. Well, you will be careful how it is being added. First is added with the fourth is equal to second is added with the third. You have to remember like that. Therefore here when I add like that, A plus B is equal to B plus A, it is true, therefore it is reflexive. When I want to prove that it is symmetric, then I have to take A comma B belongs to related to C comma D. I have given write the equation A plus D is equal to B plus C. Again let me check whether C plus D is related to A comma B. Once again I am getting C plus B is equal to D plus A. It is true because both the equations are same, therefore it is symmetric. We are checking whether when I replace them, the position, I am getting the same relation without any disturbance. Therefore it is symmetric. Well, I am taking three elements now. First is related to the second, and second is related to the third. Therefore first is related to the second, therefore A plus D is equal to B plus C. Second is related to the third, therefore C plus F is equal to D plus E. Check out how it is added. First is added with the fourth number and second is added with the second number. Now when you add both of them, I am getting in the left hand side A plus D plus C plus F, right hand side B plus C plus D plus E. I can cancel like terms in both places, then I will get A plus F is equal to B plus E, which means that AB is related to EF. For I started with first related to the second, second related to the third, I have proved that first is related to the third. Therefore R is transitive and it is an equivalence relation. We have proved it is reflexive, we have proved it is symmetric, we have proved it is a transitive, therefore it is an equivalence relation. Well, success is dependent on efforts. All the best. Thank you.